The recent observations of the interstellar object 3I/Atlas, conducted on November 11, 2025, have added a new layer of intrigue to an already puzzling visitor to our solar system. Using the Nordic Optical Telescope at La Palma, equipped with a 2.56-meter primary mirror capable of producing high-precision imaging, astronomers David Jewett and Jane Luke captured detailed photographs that surprisingly revealed a single, intact body with no visible evidence of fragmentation. This in itself is noteworthy, because 3I/Atlas had passed through Perihelion only 2 weeks earlier, an orbital phase where natural comets often experience structural stress, rapid sublimation, and in many cases partial or complete disintegration. Yet 3I/Atlas appeared to show no such signs of breakup, retaining a coherent structure that directly contradicts what would typically be expected from a comet undergoing such intense solar heating. The glow enveloping the object, however, displayed a pronounced elongation that projected to a position angle of 106 degrees, plus or minus 10 degrees. This orientation aligns closely with the sunward direction, measured at approximately 115 degrees, and mirrors the behavior seen in previously recorded images from the Hubble Space Telescope on July 21, 2025. That earlier Hubble image had captured an anti-tail, a stream of dust that anomalously points toward the sun rather than away from it, an unusual trait previously analyzed and reported as one of the object's notable peculiarities. Moreover, the new November observations included a second, weaker asymmetry at a position angle of 301 degrees, consistent with the projected anti-solar direction of about 295 degrees. This combination of sunward and anti-sunward dust structures would be remarkable for any comet. But in the case of an interstellar body with an already complex observational history, they further complicate efforts to interpret its physical behavior. At the time of these observations, 3I/Atlas was positioned 1.43 astronomical units from the Sun and 2.16 astronomical units from Earth, distances that place it in a region where solar radiation is still strong enough to drive substantial sublimation in typical comets. The field of view captured by the telescope covered an area roughly 500,000 kilometers across, providing a broad observational context within which any extended features, plumes, jets, dust tails, or debris clouds would be visible. Curiously, however, the dramatic long-range jets that had been observed in wide-field images only days earlier did not appear in these R-band filtered images. The likely explanation is that the R-band filter prevented most gaseous emission lines from being detected, leaving primarily dust-reflected sunlight visible. This suggests that the prominent jets previously seen may have been dominated by gas emissions rather than dust, making them difficult or impossible to capture with the filter used for this particular dataset. The absence of those jets in this dataset does not diminish their reality, however, as earlier wide-field imagery taken on and around November 9th had documented extraordinarily long structures, staggering plumes extending nearly 1,000,000 kilometers sunward and more than 3 million kilometers anti-sunward. Such immense jets imply persistent, high-velocity outflows that would need to last for weeks or even months. For a natural comet at the heliocentric distance of 3I/Atlas, the expected outflow velocity is roughly 0.4 kilometers per second, a speed comparable to the sound speed in the gas produced from sublimating volatiles. If the jets observed indeed extended to such extraordinary distances, then at 0.4 kilometers per second, they could not be the result of a brief or transient event. Rather, they would require at least 1 to 3 months of continuous emission to reach the detected lengths. Natural comets rarely maintain such long duration, consistent outgassing at those levels, especially without undergoing fragmentation or surface collapse. Thus, the survival of 3I/Atlas as a single body while producing jets of this magnitude stands out as a major anomaly. Adding to the puzzle is the estimation of gas density within these jets. Calculations suggest that at a distance of 1,000,000 kilometers from the nucleus of 3I/Atlas, the mass density of the solar-punched, sunward-facing jets was on the order of several million proton masses per cubic centimeter. Combining this density with the measured outflow velocity yields a mass flux equivalent to roughly 5 billion tons of material expelled per month per square area of 1 million kilometers on a side. These staggering numbers imply a level of sustained energy input and material loss far beyond what would be physically plausible for a natural comet of the size inferred from Hubble data. Typical comets have surface patches of volatile material that sublimate. However, these volatile deposits cover only a modest fraction of their total surface area. That makes it nearly impossible for a small body, especially one under 6 kilometers in diameter, to generate months of intense, directional gas flow without destabilizing. The energetic requirements further deepen the mystery. To sublimate approximately 5 billion tons of carbon dioxide ice over a span of 1 month would require about 3 times 10 superscript 1 joules of energy. At the perihelion distance of 3I/Atlas, the Sun provides around 700 joules per square meter per second. To absorb the necessary energy from sunlight, an object would require an effective sunlit surface area of at least 1,600 square kilometers. The surface area equivalent to a sphere roughly 23 kilometers in diameter. But Hubble observations place the maximum diameter of 3I/Atlas at only 5.6 kilometers, far too small to provide the absorbing area needed. If the outgassing were driven instead by sublimation of water ice, which requires more energy per gram than CO2, the required effective diameter would rise to an even more implausible 51 kilometers. These contradictions make it clear that the observed jet strength and persistence cannot be explained by conventional sublimation from a small, natural cometary nucleus. Comet researchers have encountered similar paradoxes before, but always with natural explanations involving fragmentation, multiple active sources, or dust illusory effects. In this case, however, the data clearly show no fragmentation, and the persistence and symmetry of the jets conflict with any scenario in which the jets originate from randomly distributed surface patches on a small nucleus. This leaves researchers with a challenge. Either they must stretch traditional comet theory to fit these incompatible numbers, or they must consider alternative interpretations that do not rely on ordinary sublimation physics. As has happened with past interstellar objects exhibiting anomalous behavior, some observers seem eager to explain away the contradictions by appealing to traditional models, even when the data strain those models beyond reasonable credibility. The situation calls to mind Einstein's reminder that while knowledge may tell us the rules as we believe them to be, wisdom involves the willingness to reconsider them when evidence demands. One such alternative interpretation involves the possibility of technological activity. If 3I/Atlas were not a natural comet, but instead contained engineered systems capable of controlled thrust, this could account for the sustained directional jets that appear to push material preferentially toward the Sun. A spacecraft employing thrusters that expel mass sunward would gain acceleration away from the Sun, a maneuver useful for increasing outbound velocity after a gravitational assist. Such post-perihelion propulsion would be entirely consistent with artificial mission design and inconsistent with natural comet dynamics. Moreover, the precise alignment of the sunward jets with expected thrust vectors and the absence of fragmentation under extreme energy loads would more easily fit an engineered structure than a fragile, ice-rich nucleus. The idea does not claim certainty, nor does it assert that the object must be artificial. Instead, it emphasizes that when observational data repeatedly conflict with established models, when required energy budgets exceed plausible comet sizes, when jets persist for months without fragmenting a small nucleus, when directional emissions behave more like controlled exhaust than chaotic sublimation, then intellectual honesty requires keeping multiple hypotheses on the table rather than narrowing prematurely to one that cannot fully explain the evidence. The anomalies of 3I/Atlas are not minor. They are substantial, repeatable, and energetically inconsistent with natural comet behavior. Ignoring them in favor of familiar explanations may be comfortable, but it is not scientifically rigorous.